Welcome back. This is Mr. Hyatt continuing the Chapter 2 flip on molecules and ions. We've got a couple different topics to cover in this flip. We're going to start off talking about the big picture types of bonds. We'll give both of these types of bonds more specifics as we roll through the class. But at the base level, we've got covalent and ionic bonds. And when you see a covalent bond, really tune into this co part of it. The two atoms are going to share electrons. Sometimes that electron is going to be around one atom, sometimes around the other atom. So a good example of a covalent compound is water. So if you picture an O here and an H here and an H here, those electrons are going to buzz around all three of these atoms, and that's going to cause the bond. That sharing is what causes the bond. And that forms a molecule, one molecule of water. The other big type of bond that we'll talk about is ionic bonds. And those are due to a positive and a negative attracting one another. In ionic compounds, one of the atoms is going to donate an electron to the other one. It's going to give it up. If I give up something negative, I become more positive, and that makes me a cation. If I accept something negative, that makes me more negative. I have a negative charge. I'm called an anion. At this point, it makes sense to transition to the periodic table, and we'll circle back to bonding once we look at the periodic table a little bit. So a couple things. We've got these things called groups or families. That's the vertical columns. And we've also got periods that are the horizontal rows. Things that are in the same column or in the same family or group are going to behave similarly. I've seen some conjecture that we're a carbon-based life form. I've seen guesses that maybe there's life out there in the solar system that's silicone-based. Silicone has roughly the same electron configuration in the outer shell anyway as carbon. All of these elements here in this group are going to behave sort of similarly. And elements that are in the same period are going to share common traits as well. So we'll talk a ton about trends here really soon. One of those important trends is how these specific groups create ionic compounds. So these right here are really likely to give up one electron and have a +1 charge. This column, they're really likely to give up 2 electrons and be a cation. Over here is the flip side. These are really likely to gain 1 and be a -1 charge. These are likely to be a -2 charge, -3 charge. Over here, we get a little bit covalent E. So that's definitely a trend that you see reinforced here kind of in text format. Transitioning a little bit to naming. And naming is a kind of a tricky thing to approach as a teacher. I'm not real concerned that I can throw a molecule at you and you can name it if it's something crazy. But sort of like memorizing the ions, the ones that are common, we need to memorize some of these ions. Like hydroxide and nitrate and sulfate and sulfite. There are common ones. And I'll give you a list as we get close to the start of second semester. I'll hand out a list that if you don't have them at that point, then maybe it's time to make some flashcards and things along those lines. So there are some naming conventions that we'll need to follow, and we do need to understand those because I might give you a name of a chemical in text form, and you need to be able to derive the chemical formula. Or I might give you a molecular formula and ask the name of it. So it's important, even though it might seem like trivia right now, eventually you'll see that the importance of it and the value of knowing these basic naming conventions. So binary is where there are 2 things. Binary means 2. So we've got 2 elements, could be ionic or covalent, and you see if we've got a metal and a nonmetal and it's going to form an ionic compound, then that's going to be a binary ionic. If it's going to be 2 nonmetals, that'll be binary covalent. Notice that we've got 2 different types of binary compounds, binary ionic compounds specifically. I'll talk about both of those here in just a minute. So we always name the cation first and the anion second. If it's monatomic, so mono means one, so the cation is going to take the name from the name of the parent element. I've got some examples on the next slide that will help that make sense. If it's a monatomic ion, let me try that again. Monatomic anions are named by taking the root and adding "ide." So potassium is the cation, chlorine is the anion. We call that molecule potassium chloride because we took the end off of the root of the anion and we stuck "ide" on the end of it. Same deal with magnesium bromide, calcium oxide. Notice we don't name this 2. That's something that from here we need to know that magnesium has a +2 charge, so I'm going to need 2 bromines to make that molecule neutral. Type 2 binary ionic compounds, the metals involved are weirder. They have more than one type of positive ion. They can give up 2 electrons, they can give up 3 electrons, they can give up 4 electrons sometimes. So we have to name which version of the ion we're talking about. So we're going to use a Roman numeral for that. And you can see here some examples. Copper bromide. Well, copper can be several different types of cation. So in this case, copper is giving up 1 electron to bromine to make copper 1 bromide. In this case, iron's giving up 2 electrons, so we call that iron 2 sulfide. Lead 4 oxide. Again, we're not naming that 2. We have to know that lead's giving up 4. Oxide needs 2 each. Oxygen needs 2 each to be complete, to be neutral. Then we're going to need 2 oxygens to cancel out the 4 donated by the lead. Like I said here, eventually we're going to have to memorize it. This table that's on page 65 is the table that I will give you at the start of the spring semester, so if you want to peek at that, and that's a good reference. If you get into naming or you get into a homework problem, you don't know what a molecule is, look at that, and that should help. If we have a covalent compound, that's our type 3 bond. So covalent, remember, that means that they're sharing electrons. Obviously, the first element in the formula is going to be named first using the whole element name. So if it's calcium, we call it calcium. If it's copper, we call it copper. The second element is going to be named as if it were an anion. So it's going to be an "ide." But here we are going to note the number of atoms present because we're not talking about trading electrons. We're talking about how many are buzzing around. But notice here at number 4, we never use mono for the first element. So here are the prefixes. We definitely need to be comfortable with those. Hopefully they make sense. They're pretty common numerical prefixes. Here are some examples. So I said on 2 slides ago that we never use mono. So we don't say monocarbon dioxide. We just say carbon dioxide. It's assumed. But notice down here, if it's not 1, we give it a number prefix, dinitrogen tetroxide. Tetra is what it means 4. So it's an oxygen. We add the "ide" to it, so it's dinitrogen tetroxide. Up here, we don't say monocarbon. We just say carbon dioxide. Sulfur hexafluoride. Pretty easy. And I'm not going to talk through these. This is posted on Canvas. There's a flowchart. I'm working on getting them printed and laminated so you guys can consult those as you work throughout the course of the classwork and naming things. And I probably won't let you use it on tests, but it will kind of help you get the patterns down. A couple of specifics, mainly acids. They get kind of their own naming convention. They're going to be recognized by the hydrogen that shows up first. If you see H something, it's probably an acid, and that means something specific, and we'll get to what that means in a chemistry classroom for something to be an acid soon. So if it does not contain oxygen, the acid is named with hydro and the suffix "ic." So there's no oxygen in any of these, so it's hydrochloric acid, hydrocyanic acid, hydrosulfuric acid. If there is an oxygen, then that changes things. So the ic is still added. I'm sorry, I have a head cold. The ic is still added, but we don't use the hydro because there's oxygen in it. So it's just nitric acid because this is a nitrate, and you replace the 8 with ic. So nitric acid is HNO3, sulfuric acid H2SO4. Notice we had hydrosulfuric acid that's H2S, no oxygen. And we have sulfuric, there is an oxygen, so we don't say hydro. And an acetic acid, you see right there, that's essentially vinegar. If the anion ends in ite, we're going to end the acid name with OUS. So compare nitrite makes nitrous acid, nitrate makes nitric acid. So again, little things, but that can really throw you off. If you're reading a free response question and it talks about nitrite becoming an acid and asks you to do things with it, and you call it nitric acid because that's the only nit acid you know, then you're going to be in trouble. It's going to be hard for you to get that question correct. And there's a naming convention, naming flowchart for that convention as well. So I'll post this, like I said, to Canvas, and hopefully you can access it that way. So I hope that makes sense. We'll talk a lot more about periodic trends and naming as we move through the semester.